Hello everyone, I am Princy Patel. Welcome to my YouTube channel. Today we are discuss about the topic of digital electronics. My topic name is ALU optimization. Welcome to the section where we explore how arithmetical logic unit or ALU optimization plays a critical role in design and efficiency of secure voting systems. What we are looking on the slide is modern voting booth emphasizing the importance of speed, accuracy, and reliability. To achieve these qualities, we use K-map, which are essential tools in digital logic designed for minimizing Boolean expressions. The minimization directly affects how effectively an ALU can perform in tasks such as counting votes, validating inputs, and processing logic operators in real time. Let's begin with the basics. What exactly is an ALU? An arithmetic logic unit is the heart of digital computation. It performs all the core arithmetic logic and operation within a computer system. In the context of voting system, ALU play a critical role in processing inputs such as vote data and executing logic-based decisions with system are digital and ensure reliable voting. It also highlights the importance of optimization by improving the ALU's efficiency, whether through the hardware improvements or logic simplification, we can enhance overall speed, accuracy, and reliability of the K-map work organizing truth table values into grid format where adjustment cells represent values that differ by only one bit. This let allows us to easily group terms and identify prime implements, the fundamental building blocks to simplify. Let's break it down. Visual method. K-maps offer a graphical way to simplify logic, making it easier to support randomization than using algebraic manipulation. Simplification. By minimize logic expression, we reduce the number of gates and components required, which leads to faster and more efficient ALUs. ALU design. The simplification are key optimization ALU function which directly translate to better perform in system like voting machine that really speed on that reliability. This slide introduced the concept of implementing a voting system's core logic using the principle of Boolean algebra. Implementing a voting system ALU with Boolean algebra. Think on its designing the brain of simple voting machine. Our goal here to define the rules how votes are counted and how winner determined using the logic expression. Well, follow a structured three-step process. First, we'll define the logic, translating voting criteria. For instance, that continuous majority win into precise Boolean expression. We will take this expression and represent by entire voting logic in truth table. This table will systematically show all the possible combination and represent out K-map construction for the voting system ALU. The process involves mapping the output values from our truth table or to the K-maps grid. The arrangement of this grid static allowing easily identify adjacent cells that differ by only the variable. Then comes the grouping stage. Here we are look for the largest possible rectangle groups or edges ones or zeros depending on the words we are simplifying. These groups must be powers of 2 in size like 1, 4, 4 like 1, 2, 4, 8 and so on. ALU circuit design from simplified Boolean expression. How the conversation involves selecting and arranging fundamental logic gates. We'll utilize gates like AND, OR, and NOT, which form the building blocks or digital circuit. Depending on the complementary of voting logic, we might also employ other gates such as XOR or simplify functionalities. The goal here is to construct circuit using these gates that precisely mirrors the behavior defined by our simplification optimization techniques and considerations. Our goal isn't just to have working ALU but an efficient one. One key except is minimize number of logic gates used in circuit. Fewer gates translate directly to reduce hardware complexity, lower manufacturing cost, and importance decreased power consumption. First is minimize gates. Second is don't care condition, and third is threats. The next is simulation and testing. First is test scenarios. It's like different voting conditions. Second, verify, like compare with expected results. And third is simulate using software. Now we talk about advantages and disadvantages of K-map approach. It's fundamentally simple, visual, and relatively easy to understand, especially for a small number of input variables. It's important to acknowledge its limitation. As the number of variables increase, K-map becomes significantly more complex to manage. Being a manual process, it can also prone to human error. Multi-bit voting system. There are two types: 5-bit voting system and threshold voting. ALUs and voting system can operate a larger of bits. The principle remains the same, but complexity don't care. Don't care conditions. This slide installation the concept of don't care condition in the context of K-maps. This arise when certain inputs combination are invalid and don't influence the desired output. In our K-map, these are marked with the X during K-map grouping. We can treat this don't care either 0 or 1. Error correction methods. Voting logic in error correction. Voting logic isn't just for election, it plays a vital role in error correction within digital system. Consider human code where extra rounded bits are added to data to detect and correct, and majority vote determines the correct output, effectively masking errors. As you can see, the principal majority voting that we have discussed as fundamental in various error schemes, ensuring the data intelligibility and system reliability. Now, optimizing ALU for complex function. First, K-map limitation, which is like a simple K-map may not be enough. Second is threshold logic units. Output depends on the weighted input, some surprising a threshold. Third is weighted majority. Each input might be weighted. Advanced optimization techniques. First is Quine-McCluskey, that automatically simplifying Boolean functions. Second is Espresso, that optimizes digital circuits for area and latency and power optimization. Complex system can introduce latency or delays in processing the word. Similarly, the circuit complexity directly impacts power consumption. Therefore, the logic optimization is crucial to reduce both delays and power uses. Fault tolerant and voting in ALUs. First is redundant system and second is fault detection. In redundant system, ALU uses majority voting to decide the output and the input intensity. Threshold, threshold logic units or TLUs produce one output only when the weighted sum of their inputs exceed specific threshold. This approach can be particularly helpful in managing K, K-map complementary for the system with the large number of threshold logic with. Instead of simple binary inputs, each input can have associated weight. The LUS then calculates a weighted sum of their inputs. To make a decision, the weighted sum is compared against the predetermined threshold value. For instance, in 3 out of 5 voting scenarios, the threshold would actively be a 3. The LU would output 1 only if the sum of active inputs. Conclusion and future work. We have explored key areas including ALU optimization, K-map design, and the implementation of voting system using Boolean logic. Looking towards future work, there are exciting avenues to pursue. This includes investigating more complex voting algorithms, layering, and advanced optimization techniques, and ultimately pursuing the actual hardware implementation of this voting system ALUs. Now, friends, this includes valuable discussion found on the platform like Stack Overflow and Electronic Stack Exchange, particularly those related on ALU design and Boolean simplification techniques. Additionally, I drew up upon articles and tutorials available on websites such as Geeks for Geeks and All About Circuits. This resource provide key insights and information throughout our exploration of implementing voting system ALU with Boolean algebra. Thank you. It's